Hi, this is Chapter 8 Summary Notes on Gases. This video involves Gay-Lussac's law. All right, in Gay-Lussac's law, we're looking at pressure varying directly with temperature. All right, and again, this goes back to the ideal gas law, PV equals nRT. All right, and again, we're dealing with pressure, and we're dealing with temperature this time. The other terms are kept constant. Volume and number of moles are kept constant, and the R is a constant value. So you see in the working formula down here that the pressure term is over the temperature term, and same thing with the second set of conditions. The ideal gas law represents one set of conditions, but when we set one set of conditions equal to the second set, we come up with a constant that's very similar to what we saw in the Charles law video that is also a direct relationship. So we know that the temperature can also be on top if we need to solve for a temperature term rather than a pressure term, which makes this very convenient. That either way you look at it, a constant is developed between the first set of conditions and the second set of conditions. All right, so it says the first little problem here asks us to solve for P2, so just getting some more space here in which to work. All right, so if we start with either one of these, let's start with the P2 in this first one because that makes it very simple. We want to get rid of the T2 term, so we need to multiply both sides by the inverse of that. So let's go ahead and do that. All right, we're going to take T1, T2 that's on the bottom. P1, P2 is on top. All right, so we want to multiply by the inverse of what we're going to get rid of. T2 over 1. I hope you remember clearing terms from your math class. All right, that gets rid of T2 on that side. So our final formula is T2 times P1. Oh, what did I do? T2 times P1 is going to equal P2. All right, and we need to get our T1 term on the bottom. T1. Okay, so we've basically just moved the T2 to the numerator position on the other side, which is fine. All right, so you can do that. And again, you don't need to memorize formulas. If you know your ideal gas law, then you can clear terms and just get the working formula for any problem that you need to solve. All right, so let's try problem here. And again, let's make some more room. All right, we'll assign variables. Pressure, the first pressure is 2 atmospheres. The first temperature is 18 degrees Celsius. Remember to add 273 to that right away. Okay, and if we do that, we've got 11, 9, 291. All right, so it's asking us to solve for a new pressure. And the temperature is now 62 degrees Celsius. All right, and again, we need to add that. So we get a 5, 6 and 7 is 13, carry a 1. So we get a 335. Okay. So far, so good. Remember this Kelvin temperature. I think I need a little more room here. Let me just scroll down a little bit further. All right, so if we're solving for P2, again, we can predict what's going to happen if this is a direct relationship. If the Kelvin temperature is increasing, then the pressure also needs to increase. All right, so the temperature is increasing, so we want the pressure to also increase. All right, so let's go ahead and set up our formula. T2 over T1 is going to be equal to P2. All right, let's substitute now. We have 335. Let me get it in the right pen. Kelvin over 291 Kelvin, and you can just see by that relationship it's greater than 1. I'm going to multiply that by our first pressure. and then go to the calculator. All right, so we have 335 divided by 291, and then multiply that by 2. All right, which gives us 2.30 as our second pressure. So did it go up? Yes, it did go up. And that's how you work a Charles Law problem. All right, so here's another one. All right, this is in torr, but that doesn't make it any harder or different. It's just using a different pressure unit, and we can still solve it the same way. All right, because the pressure units are going to cancel. So take a moment, you try this problem, come back and check your setup and your solution. All right, I hope you're looking at your answer and checking your work here. My first pressure is 645. The second pressure is 824 torr, and it is increasing. All right, so the temperature will also increase since this is a direct relationship, and you can see that by my arrow up over here, my prediction. All right, the first temperature is 128 plus 273, and that's 401, all right, which I already applied in the formula. And we're solving for T2 in degrees Celsius. It's asking us to solve in degrees Celsius, so we have to solve for Kelvin first. So that's real important that you keep that in mind. All right, so if I'm multiplying, you can see over here on the calculator display the temperature of 401, then that gets multiplied by 824, divided by 645, which brings me to the 512 Kelvin. All right, and then I can come back and subtract 273 from that in order to get my 239 degrees Celsius. And did my temperature go up like my pressure went up? It went up from 128 to 239. So yes, the prediction held true. Okay. All right, so that's how to work a Gay-Lussac's problem. All right, where we're dealing with pressure and temperature, keeping moles and volume constant. All right, just a couple of conceptual things to finish up with. Vapor pressure and boiling point. All right, we see in the picture here, and I'm going to enlarge it so you can see a little bit better. You'll see the thermometer. This is just some water boiling over a Bunsen burner. It's showing 100 degrees Celsius. This is known as normal boiling point. Because we can get things to boil if we adjust the pressure at different pressures, we can get water to boil. But at 761 atmosphere, sea level atmosphere, when the atmospheric pressure inside these bubbles equals atmospheric pressure, that's when we get water to boil. All right, so it's just water vapor inside those bubbles. Water's not breaking down into hydrogen and oxygen. Now, that'd be mighty explosive. All right, so our temperature increases to the point at which the vapor pressure in the bubble equals atmospheric pressure, and that's when we can get boiling. All right, the other picture here has to do with an autoclave. It's like a large pressure cooker that's used to sterilize equipment in the medical field. All right, so at home you might have a pressure cooker. And a pressure cooker, maybe you do canning at home, and it might have a gauge on it. It might have a weighted rocker. And those weighted rockers can be anywhere from 2 atmospheres to on up. But we're looking at this area right here on this chart to see that the temperature of the water inside the pressure cooker can be as high as 120 degrees Celsius. All right, our normal atmospheric pressure when water boils is 100. All right, then remember this is the same as 1 atm. But again, when we do canning or pressure cooker and you're at 5 pounds per square inch or 15 pounds per square inch, I should say, then you're generating 2 atmospheres of pressure inside the pressure cooker. Okay, so that brings that boiling point up to 120. And so that's why your pressure cooker cooks your food very, very fast. It breaks down the muscles and fibers inside meat to make them nice and tender. All right, so that's just a little bit of conceptual information about pressure and temperature combinations. And this was Gay-Lussac's law, pressure and temperature directly related when moles and volume are kept constant.